Starting with questions from 3-6. Does anybody have questions from 3-6 that we want to talk about? Elena? 23.
Did you bring your big pen?
No, I forgot it.
I knew it.
Okay. So start with the first derivative. To do that, what do we need to use to differentiate x squared natural log of 2x? Not yet. Product first, right? So that's going to be x squared times the derivative of natural log 2x. To do that, we need to use the chain rule, right? And then I have plus the derivative of x squared times the natural log of 2x. So if I simplify that down, let's see, 2's cancel, x cancel, so I'm left with just x plus 2x natural log 2x, right? So that's y prime. The second derivative then, to differentiate x, well, that's just 1. To differentiate 2x natural log 2x, I need to use product rule first, right? Because the multiplication in between. So that's going to be 2x times the derivative of the natural log of 2x, which is 1 over 2x, times the derivative of 2x. And then I have plus the derivative of 2x times the natural log of 2x. So again, we do a little reducing, and I have 1 plus 2, that's 3, plus 2 natural log 2x. And I suspect that's probably what they have for you. Yes?
Where is, like the y double prime, where does that 2 come from with the 2x and 1 over 2x?
So the 2x is here. The derivative of the outside is here. That's the derivative of the natural log 2x. And then the derivative of the inside is there.
Okay.
Is that
Yes.
the highlighting help?
Yeah, that's.
And again, like, at this point, we've abandoned like writing f of g of x and like doing all the notate for the chain. We're just like seeing them when it's, especially when it's a simple, chain rule situation where the derivative of the inside is easy to mental math it, right? I've just been skipping writing that notation and just doing it. And that's okay?
Yes.
Okay. And you feel good?
Yes.
Was that those were the answers, I'm hoping?
Yeah, I believe so.
Okay.
That works.
You guys are all, I think, do a really good job of making sure you're checking things as you go. So I count on you guys to, when I do one of these, to double check me. What else do you guys want to talk about from 3-6? Elena?
49.
Sure. Overall, was this seemed a little easier than maybe the previous couple of sections? Good. Yeah, I think so. I think 3-7 and 3-10 are both pretty easy ideas.
Oh yeah, Monday.
Wednesday review.
Okay.
Mr. Klug, are you going to give us a lot of like MCQs again?
Yeah, in fact, I've already put them in. If you look under the test, you can see the,
Oh, perfect.
and there's like 60 of them or whatever.
Can we print them up again?
No. Unless I get recruited.
I'll go with you.
All right. So we want, it says use logarithmic differentiation to find the derivative. Okay. So we take the natural log of both sides. Again, you don't have, well, I guess you do kind of have to do it that way. Oops. So I did that to both sides. First logarithmic property I'll apply is the power property that allows me to rewrite that exponent as a coefficient, because there's no multiplication or division going on inside that logarithm, so we just go straight to the power property. Now I can apply, or take the derivative of both sides. So the derivative of natural log of y is going to be 1 over y dy dx, because I'm doing like an implicit differentiation here. And now it's going to be a product rule derivative, because I have 1 over x times the natural log of tan x. So I have 1 over x times the derivative of the natural log, so that's going to be 1 over the insides, times the derivative of the outside, derivative of tangent is secant squared, plus I have the natural log of tan x times the derivative of 1 over x, which again, I'm going to think about 1 over x as x to the negative 1. So when I do the derivative, I get negative x to the negative 2. So let's see here. Probably try to do some,
That whole like right side is the product rule, right?
Yes.
Okay.
Let's try to do some trig cleanup here. So 1 over tangent is going to be cosine over sine, right? Secant squared is 1 over cosine squared. So I can nix those. So I'm going to write that as cosecant x times secant x all over x plus, well, actually, let's do minus because we have that negative sign right here. Natural log tan x over x squared. And let's make a common denominator here. So I'll put an x there and make an x squared. So dy dx is going to be x cosecant x secant x minus natural log tan x all over x squared. And when I multiply by y, then I get times tan x to the 1 over x. And I'd probably just leave it that way. I might write it all like as a single fraction or whatever, but the numerator I'm just going to put in a bracket and times tan x or tan x to the 1 over x, and I would stop. I don't think that, I don't know, we're not going to get any nice simplification to happen after this point, so it's just like, what are we doing? I don't know. Does that feel okay? Pierce.
Where did you get that x to the left of cosecant x? Where did that come from?
Me just making a common denominator.
Oh, okay.
So I could add the two fractions. Isabel? 19? Sure. Okay. So we're just asked to find the derivative here. to do that, what derivative rule do I need to use first? What? This is just a chain, right? No multiplication is going on
Oh, yeah.
outside of the logarithm.
Wow.
All the multiplication is going on inside. So first thing we have to do is a chain rule. So that's going to be 1 over the insides times the derivative of the inside. So what's the derivative of e to the negative x? E to the negative x times the derivative of negative x,
One or negative one?
negative 1. Right? How do I do the derivative of x, e to the negative x? Product rule. So I'm going to have x times the derivative of e to the negative x, but I already did that. So just copy that again. And then I'll have derivative of x times e to the negative x. So far, so good. Let's combine some like terms. So I have a y prime is going to equal negative x e to the negative x over e to the negative x plus x e to the negative x. Which is pretty gross, but let's do this. What am I going to get if I multiply the top and bottom by e to that x? What's e to the negative x times e to the x give us? 1. So I just have negative x on top. Same thing happens down here, right? The other way was not incorrect. They just more, just some sneaky simplification, right? If it's a free response problem, I would have accepted the previous answer before I multiplied the top and bottom by e to the x. I'd have given you full marks for that. But if it was a multiple choice question, that's not going to be one of the choices. Well, again, it sometimes can be the hardest part, right? Like here, the derivative often is not that difficult. Often, though, the algebra to get to simplest form is kind of a bear. Now, they're not going to make you do that every single time, but they're going to take advantage of the multiple choice questions to check to make sure that you can do that reasonably. By and large, when I look at the multiple choice that I've looked at, only occasionally do I run into something where it's like, woo, that was some tough simplification right there. More often than not, it's pretty obvious what they did, or pretty minimal. But I would say, like, on a problem like this, it's probably 1 out of 5 times that you run into something where the simplification is not obvious, which isn't so bad, right? Because this is probably, problems like this are probably only like 10% of your multiple choice questions. So it's not, we're not even talking that many. You might run into 1 or 2 where the simplification is rough on the exam, period.
Why were you able to
Okay. Good, that's the halo effect,
Yeah.
right? When you come ask Mr. Kulik a question, you stand near him. Like the halo of my math knowledge sometimes answers the question before you can even get to it. All right. Should we get along with today?
Yes. Yes.
All right. So 3-7, this is all I have. I have one example problem because there's no new content in 3-7 for you guys. It's just going to be like, hey, do some story problems that involve using calculus.
Oh, so now I see what you said. It's reasonable.
Yeah.
Now I get it.
Oh, sorry. In natural and social sciences. I've skipped like the problems I picked are almost all like physics or geometry-ish related questions. So they're gonna feel relatively familiar for a lot of us that have taken physics and stuff before. But this is also the kinds of questions that the AP tends to. Not every question has this many parts, guys. Yeah. But here's the good part, is that most of them are so simple, right? Part A, what's the velocity as a function of time? Yup. Which is, tell me it.
2t squared.
So it's not a good game.
3t squared, you mean?
Oh, oopsie, sorry. 3t squared minus 12 plus t. Right? Or plus, oh. Wow.
Rusty. But what did that take?
Well, if I did it right.
Yeah, like 10 seconds maybe, right? Part B says, what is the velocity at 2 seconds?
Plug it to.
So what is that? That's positive 12, negative 24, positive 9, that's negative 3, I agree. After 4 seconds,
48.
yep, 48, minus 48, plus 9, right? Again, now, if I'm on the AP exam, and that's a question in a calculator section, I am not risking doing any of part B by hand. What I would do is I'd type in the original function given to me into my calculator, into the y equals menu. I would exit out to the y equals menu, and I would press the math button. I will scroll down till command 8, that is called nderive. I will do the derivative with respect to x of vars, y vars, function y1 when x is equal to 2.
Basically, we can do this all the time.
Like anytime we just ask for a derivative, what?
No. So it only will do it if you're plugging a number in. Right? And now look at the number that we got here. What was our actual answer? Negative 3.
If you go negative 2.9, then they mark you down.
Probably.
Yeah.
But again, you should recognize like, yo, I'm plugging an integer into something that's all integer arithmetic. I should be getting an integer back. And I can do the same thing then. I can just update that and change it to a 4.
What situation would be faster?
Well, this is what this is it's safe, right?
Yeah.
Because I can't screw up any arithmetic. But this is also but this is also why I'm showing you how to use it. Now, I will tell you on the calculator sections, there will be problems where they intend for you to type the function in and plug it into your calculator because taking the derivative of it stinks, and then plugging the value back in really stinks to try to do it by hand. There's going to be problems where they want you to do this.
How do you just look at the problem? You're like, this looks way too hard to do by hand. So I'm just
Well, if it's a calculator section,
and you're just like,
your first thing you should be thinking of is, can I do this in my calculator or should I do it by hand? And if the answer is, can I do it in my calculator, it's probably they're asking you to do it, giving you the calculator option for a reason, right? Yeah. So all I did is I went to the y equals menu and typed in my function, my original function. Everybody's okay there? Once I've done that, I went back to the main screen. I pressed the math button, and the command I'm looking for is nderive. So I select that. Now I have to fill in what variable am I taking the derivative with respect to. I used x's in my equation. I need to write my equation in. Now, I never type it in. You could type it in that spot also. I like to put it into the y equals menu because if I have to get points on that later on, if I'm making like a tangent line or something, like it just often saves me some steps to do it that way. But I press the vars button. That's vars is short for variables. I want the y1 variable, so I go to the y variables here at top. We're always going to be in function mode in this class. So I'm going to pick the y1. And then I tell it what value of x to plug in. So like 2. And it does it. Okay. It then asks, when is the particle at rest? What do I need to do to find that? Set what equal to 0? The velocity, yes. Right? Particle's not moving if its velocity is 0, right? If its position is 0, that doesn't tell you if it's moving or not, right? Okay, so we're just solving 3x squared minus 12, or 3t squared minus 12t plus 9 equal to 0. How do you solve an equation like this? You could use the quadratic formula. You could try to factor this. You could graph it and find the 0. Any of those are fine, right? If it's a no calculator, obviously graphing goes out the window. But the quadratic formula, you still know. Do we remember the quadratic formula? Negative b plus or minus square root of b squared minus 4ac all over 2 times a. That's why we're bothering to say it again. So 144 minus 108 is 36 over 6. So I have 12 plus 6 over 6. That's 3. Or 12 minus 6 over 6. That is 2. No, that's 1. Can you check this?
Plug it back in.
Yeah, so I'll just, on my calculator, I'll just try the derivative when x is 3, see what I get. What's that mean?
0.
That's basically 0, right? That's 0.000001. I'll call that 0. If I do with 1, I get 0 again, right? So I feel good. Everybody happy? All right. Let's see what's next.
Could you go back? What were the answers for the quadratic?
3 and 1. Yep. Part D says, when is the particle moving forward, that is in the positive direction, and when is it moving backwards? So you want to know when the derivative is, the velocity is positive, that means it's moving forward, or when it's negative, right? Now, again, you could say we could graph this. What would you do if you didn't have a graphing calculator? I would draw what's called a sign diagram. So what I'm going to do is I'm going to pick a test value from things that are less than 1, things that are between 1 and 3, and then things that are bigger than 3, and see what the velocities were in those cases. So here's the beautiful part. At 0, what is the velocity got to be? 9. At 2, what's the velocity? We already found it. It's negative 3. And at 9, what is the velocity? Or at 4, what is the velocity? 9, we already found it. So what am I seeing? If I found the only places where the where where a velocity can change from negative to positive, the zeros, I know everything less than 1, the velocity is positive, and everything bigger than 3, the velocity is positive, and then everything between 1 and 3, it's negative.
Wait, how do you know though that it's not changing direction at like x equals 0.5? Because I thought I did on the last test and it said that you could
Because we found the only places where it's 0,
Yeah.
because it's a continuous function.
Oh.
If we know we crossed, the only place we cross is at 1 and 3, you can't at somewhere
Okay.
0.5 go negative because you'd have to have another 0 in there, but we don't. Oops. That should be, those should be parentheses though, right?
What's the thing right before the x?
That's the symbol that says for all. It's like an upside down capital letter A.
What I thought it was.
That's a mathematics symbol. You'll see it at some point in your mathematics classes. As you go further along and take more and more serious mathematics classes, you get more and more weird symbol notations because you know what mathematicians are?
Nerds.
Thank you.
I mean, it's not a bad thing, guys.
Lazy.
Really?
I'm going to draw a 1 symbol to replace 2 words every chance I can. I'm going to create all kinds of goofy looking symbols to replace common phrases because I don't want to have to write down as much
Like
stuff.
the 3
Why do
dots
they
for
pick
like
that?
therefore. What?
Like, why did they pick up upside down?
I don't know the history of the symbol.
Why did they look at 3 dots instead of just like therefore?
Yeah, like.
Whoa, 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 that's a little closer.
So 3 like the these 3
That symbol there is for there exist,
Where do you draw?
Yeah, wait.
the backwards E. And if you put an exclamation point after it, means there exists a unique.
There's too many.
So,
Yeah.
Perfect.
So
This one wasn't enough.
what?
It is, the whole language.
Do I know it? Yes. Do you? No.
Did you take a class where you had to learn this language? I feel like that's a class.
No.
Oh.
You're just expected to kind of pick it up as you went.
Is triangle 3 dots?
Yes.
What is that upside down?
That's the symbol for all. That's just a mathematical abbreviation because I try not to use it in the lower level classes because it becomes overwhelming.
Good
But
idea.
but you guys are now. I'm looking at a group of students that in all likelihood are going to take at least 1 calculus class in college. Right? So
Right now.
as you get further along, you're going to see more and more of this notation. Your professors will expect you to be familiar with it. I am just trying to slowly integrate some of that stuff along the way so it's less of a shock to you later on where you're like, oh, I remember Mr. Kuril talked about this. That just means for all. And you can whisper that to the person next to you goes, what is that symbol? Okay? Yes, go ahead.
I just don't get where that X equals 4 came from. I got the rest.
So what I did is I picked a test value
Yes.
somewhere between 0 and 1, between 1 and 3, and bigger than 3. Does it matter what numbers I picked in those intervals? No. I was being efficient when I chose 0, 2, and 4. 0 is easy to calculate, and 2 and 4 we already did in Part B. So I could recycle my work. I didn't have to plug it back in. I had those numbers already.
Okay.
It's almost like the problem knew that you're going to need those numbers later on and made you get them earlier so you didn't have to do it again.
Okay.
Everybody's okay?
Yes.
All right. And again, if you had your calculator on this problem, you could just graph and look at the picture, right? And see where it was above the x-axis and where it was below. Now, again, every time we do one of these things, I'm going to talk about how to do, at least talk about how you could do it either way. because we can't count on things having calculator because that doesn't happen every
Do you
time.
think on like a problem like this, we would have a calculator, or do you think this would be like no calculator? Like,
I've seen it go either way. It depends on how inconvenient the arithmetic would be.
okay.
If it was one where you're going to get like, you know, like the square root of 2 or something in your answer, like if your zeros were irrational, or maybe the coefficients on this quadratic were decimal or something, like I could see it being a calculator question if they made the arithmetic really inconvenient. But probably it's a no calculator question, since most of this one we're looking at now, because the arithmetic is all whole number. All right. E says draw a diagram to represent the motion of the particle. So what would we say here? Okay, let's say at t equals 0, we are at position 0, right? Actually, let's draw that in color. And we go forward all the way until we get to t equals 1. And at t equals 1, the position there would be 1 minus 6 plus 9, so 4. At that point, we turn and start going backwards all the way until we get to time 3, at which case the position there would be, let's see, 27 minus 54 plus 18. Oh, or I'm sorry, 827. That's 0 then. Yeah, sorry, 0. And then we twist and go forward from there on, right? So that's a diagram that kind of represents
Wouldn't have guessed. I thought we were going to draw a graph.
Nah. F. Find the total distance traveled by the particle during the first 5 seconds. Okay. So we need to do this in 2 separate sections, right? Why do I need to do this in 2 separate pieces? Because I should say 3 separate sections. The reason is because we turn direction, right? Twice. So my distance I need a distance that I travel from 0 to 1. And then I need a distance where we travel from 1 to 3. And then I need a distance where we travel from 3 to 5. Right? Everybody's okay with that? Okay. So this is going to be the absolute value of s of 0 minus s of 1. The absolute value of s of 1 minus s of 3. And then the absolute value of s of 3 minus s of 5. And that should give me the total distance traveled by my particle. Now, I know what this first number is. Who can tell me what it is from looking at the diagram we just drew above? Yep. How about for the next piece?
Negative.
So, and I know S of 3 is 0 because that's a 0. Because we're doing the absolute value of it,
Oh,
right? I just have to calculate what S of 5 is. So I can plug 5 in, or I can just go to my calculator and do y1 of 5. That's what I'm going to choose to do. I get 20. So I have 8 plus 20, so 28 units. So far, so good? Now on these, how is the calculus?
Not hard. But
Not
figuring
hard.
out what to do is harder.
Yeah, the arithmetic, again, also not hard. The tricky part is, what do we do? Yeah. G says find the acceleration at time t and again after 4 seconds. How do you find acceleration? It's the second derivative of position or the first derivative of velocity. So if I take my, where was it? There's my velocity equation. What's the derivative of that? 6t minus 12. Good. And then it's wanted it also at 4 seconds. So that would be 12, right? And then I forget, what are the units on this thing? I didn't even read this. Meters and seconds. Okay. Probably should have been writing that down. This is 28 meters then. I said units, but well, like whatever. Okay. So far, so good. So I have this guy and then this guy. And then part H wants me to do what here? Graph position, velocity, and acceleration functions on the are from 0 to 5. Okay. So let's make a little space for ourselves.
what does it say? X over 5 squared?
That's m per meters per second squared. Sorry. One, 2, 3, 4, 5. And then, I don't know, 2, 4, 6, 8, 10. I hope I don't have to do more than that. Ooh, I bet I will. Let's go by 4. Make that 20. All right. Well, let's do acceleration first. That's easy, right? So I know that a of 2 is 0. And then a of 4 is 12. So that's just a straight line. Feel good there? I guess I should probably have left some room to be negative. You dumbo. I just was hooked as I in that position function. Okay, let's do velocity in blue. So we know that at, we have x-intercepts at 1 and 3. And then we know at 2, we're at -3, and at 4, we're at 9. So we're going to be oh, I guess we could do, oh yeah, and at 0 we're at 9 for sure. So we'd have something like that. Okay with that. And then we'll do position in orange. We know at 0 our position is 0. We knew at 1 our position was 4. We knew at 3 our position was back to 0. And we knew at 5 our position was 20. And I think that was probably did one of those, because position can't be negative, right? So it kind of looks like, got to look like that, something. Yeah, Pierce?
Acceleration, since like you step the graph after, but you still.
Yeah, I should have it going this way too. Yep. In fact, that should go, that's not really very straight, is it? Should go to -12. What do you guys think? Prater? Okay, well, yes, but it can't be negative for our situation, because we know we go forward 4, backwards 4, and then we're forward after that, right? So like there's no place along the way where we could have picked up any negative position. So this particular one, yes, in general, sure, position could be negative, but ours it couldn't be. Does that, I said that I said that poorly when I was talking aloud to myself. Does that felt okay though? Okay. And then L says, when is it speeding up and when is it slowing down? What would we say the criteria for speeding up would be? Yes. So speeding up is acceleration greater than 0, and slowing down is where it's equal to 0, right? I would do the same thing. I'd draw like a little sign diagram here. But this is really easy, because what's the only 0 for a of t equals 6t minus 12? 2, right? And I know like when t is equal to 0, a is -12. And when t was equal to 4, we did that already, a was +12. So we know that from that a of t is negative for all t from 0 to 2. And then a of t is positive for all t for 2 to positive infinity, right?
We can only ask you one speeding up. Could you just write that on the part?
Oh, yes. Yes. But let's think about this a little bit further. So let's say here, this is t0, 1, t equals 2, 3, 4, 5, 6, and at that point, everything is the same, right? So from here to here, we are slowing down. And then from here on, we're speeding up, right? And this is from acceleration. If we look at our velocity, we are going forwards from 0 to 1, and then from 3 on. And then we're going backward on that section. So for example, at time 2.5, we're speeding up as we move backwards, right? So we're like accelerating in the reverse direction. Does everybody feel okay on how we kind of can describe what the particle is doing for any time?
How are you still going?
So at like 2.5, it's speeding up because it's in green, but it's moving backwards because it's in the purple.
Yeah. Like gravity. Oh, it's negative, but it speeds up.
Yeah, like if you talk about like dropping an object, it's moving down, but it's getting faster at each second.
Yeah.
Exactly. Or if you put your car in reverse and hit the gas, it's going faster in the reverse direction.
Right. So it's when it crosses zero, so then it just considers speed.
Yeah, and then like you hit brake and you shift into drive. So when you start hitting brake, it starts slowing down. You're still moving backwards until you stop and you hit the gas forward, and now it's moving forward and accelerating.
Right. Okay.
We feel okay here? All I did is I collected the information we.
So when it's going back, you know it's slowing down.
I just picked a time. I picked an Okay. So I picked an arbitrary time, like 2.5, and then I just looked at the graph that I drew here. So at 2.5, the acceleration tells me we're speeding up, but the velocity tells me we're going backwards.
Why is it not speeding up the whole time? I'm just like looking at our graph, isn't it speeding up the entire time? Or am I just like,
No, because we have this section of our velocity that's below the x-axis, right? That's negative velocity. That's moving backwards, right? And we have negative acceleration here. That's slowing down, right?
To be constantly speeding up, it would have to be linear and never cross zero. Right.
Well, for the
For acceleration.
doesn't have to be linear,
Or like.
but it has to be all above the x-axis.
Yeah, or all along. Right.
Sure.
Okay.
Yeah.
what would that have to be coming from?
So Elena, think about you get in your car.
Yes.
You put it in reverse. You step on the gas. You're accelerating in the backwards direction. You hit the brake. You start slowing down. You're still moving backwards though. Car comes to a stop. You put in drive. You press down on the gas. You start moving forward, and you're accelerating in the positive direction. You come to a stop sign. You hit the brake. You're moving forward still, positive direction, but you're slowing down now. Does that? When you think about like driving in your car, it all starts making more sense. It's like, okay, yeah, that's just like, pressing the gas in reverse, or pressing the brake in reverse, and pressing the gas in drive, and pressing the brake in drive.
Why would we know it's slowing down when it's below zero on this graph?
When what is below zero?
Acceleration. Why would it be accelerating?
Accelerating negative.
Or do we know because it's starting?
So negative acceleration.
We know it's slowing down because acceleration is getting closer to zero.
Okay.
Yes. Yes, thank you. Okay. It's 3:10.
And so is velocity.
All right. So 3:10, it's not mine either. Like I'm very good with like the theoretical and the abstract, and like I get much worse when you start dropping me into the real world.
Yeah, physics was a tough year for me.
So 3:10 is about linear approximation and differentials. Now this sounds complicated. It's not. What are we talking about doing here? We're saying, okay, say we have some curve f of x, and we know the derivative at some point, but I don't really know anything else about f of x. Well, what I can do is I can create a tangent line, because if I have the derivative at a point, I have a slope, and I have the point, so I can write a tangent line. I can then use that tangent line to approximate values for f of x, but there'll be a little bit of error associated with it because f of x is probably not linear also. That's all we're doing in this section. We're just going to write a tangent line for a function, and we're going to use it to approximate values on the function. And maybe we might ask to calculate some error afterwards, like how good was our approximation. Everybody okay with that? That's the overall idea. So like, don't let any of the symbols or the notation or whatever get you bogged down. At the end of the day, what we're doing is making a tangent line and plugging things into the tangent line. All right, so we say, okay, the equation for our tangent line at f of x is this, right? This looks complicated, but what is this really?
The change.
This is y, that's m, or like y1, and a is like x1, right? This is just the point slope form where we've rearranged it so the y is by itself. Okay? I can use that to approximate the values on our function as long as our x's are somewhere near, the x value where we found the slope. The further away we get from that, the worse our approximation we'd expect to get. But as long as we're relatively close to that value of a, where we found the derivative, this should be pretty close. We call that a linear approximation or a linearization. So, let's do an example here. We want to find the linearization of the function f of x equals the square root of x plus 3 at a equals 1. So what are we going to do here?
F and A. Dude, it's like, it's underlined. What? Oh my god.
Good job.
You guys are a bunch of doofuses. What's the derivative of f of x in this case? Times 1. The derivative of the inside. Shh. Focus, please. Focus. So f prime of 1 is going to be what is 4 to the negative 1/2? And it's not negative 2. It's 1/2. What's the square root of 4? And then make the reciprocal for the negative exponent. 1/2. Everybody's okay with that? What? 1 plus 3 is 4.
Oh, that makes so much.
And then the square root of 4 is 2, but we make the reciprocal because it's a negative exponent. F of 1 is 2, right? So our linearization is going to be y of, or f of 1 plus f prime of 1 times x minus 1. I'm just filling in to here, right? But what did I really do? I just wrote the equation for the tangent line, right? That's all I did. Just the equation for the tangent line. Am I going to memorize this linearization equation? No, because all I'm doing is writing the equation for a tangent line. Okay. So it then asks to approximate these values for the square root of 3.98. What is x equal to?
Is this calculated?
No.
Oh, x is 0.98.
Yes, 0.98. Oh. Wow.
So I'm just plugging that into my linearization.
The top, x, f, x, sure. So you did 3.98 minus 3, and then you plug it back in for x. What do you mean x? Like you find x, we're going 3 minus 3, and then you plug it back in.
You just pretty much plugged in 0.9.
Yeah.
3.98 in the situation. The square
So-
root of that is 0.98, and then you just plug that in.
What? I know, that's not what I did.
Oh, then what?
I just looked at if I have the square root of x plus 3, if I want to evaluate 3.98, x just must have been 0.98, right? Because x plus 0.98 plus 3, or x, this is like 0.98 plus 3, right?
Oh.
Which is 3.98. So x was 0.98. That's what I'm plugging into my linearization. Yeah.
Oh.
Yeah. Yeah.
Got it.
That's okay.
Thank you.
That's okay.
Sorry.
Are you apologizing to me? I didn't. Oh, that's okay.
He's very stressed out as I answered the question.
No, it was just one of those, like, there was a lot of conversation going on. I kept getting sidetracked from, like, pulling together a coherent explanation because there's a lot of other conversations going on at the same time, and I get distracted.
Yeah, I don't.
You know, it's early. So if I wanted to do 0.504 or 0.405, what is the x in that case?
1.05.
Yeah. So I'm just going to do the same thing.
Minus 1 and you added 1.
Oh, sure. Yep, that's right. Yep, so that answer above is wrong. Let me fix it real quick.
Why did we choose 1.05? Because 4.05 minus 3 is 1.05.
So that's
Unless
1995.
sure, would you always just leave it as
No way, dude.
You want to leave all of your...
just leave it exact?
Yeah.
Okay.
I thought that last section was like a homework question. Why did we choose 1.05?
Dude, because
Let him explain it.
I'm
He's
uncomfortable.
the teacher.
Because 1.05 plus 3
Oh.
is 4.05,
I keep forgetting.
right? So the last piece asks if these are over or under estimates. Well, naively, the easiest way to check would just be to type in these into our calculator, right? So what did we get? Over or underestimate? Over, right? Real close, but it's over. Everybody agree?
Yes.
And 4.05 is a...
Wait,
no.
yeah.
oh, equal.
It's over, right? This number is bigger than that one, right?
Oh,
Because the fourth decimal point is a 4 on my calculator, but it's a 5 on my paper. No,
Oh, I was rounding it. That's
never round.
Okay.
Yeah, so we put everything
When you're
back.
when you're making an approximation and then you're trying to compare whether it's an over or underestimate, You can't round
Oh.
to tell if it was an over-under estimate, because now you've destroyed any possible over-under estimating. Because if you wanted to, you just round so that they're the same,
Class.
right?
Yeah.
Can't do that.
Oopsies.
Is that okay?
Yeah.
Okay.
So you literally just like get the decimal form, whatever it gives you, don't have to plug in whatever equation.
For right now, that's naively, if we have a calculator, we can just do something like that, for sure.
Okay.
So the next question we have is, okay, for what values is the approximation the square root of x plus 3, which the linearization they're telling me is 7/4 plus x over 4. For what range of values is that going to be accurate within 0.5? And then we'll not do within 0.1 because it's the same problem. So what do we need to have?
So you can't plug it in.
We need f of x minus L of x to be within 0.5, right?
Question, on the A/B test, it's like, so you're not gonna like look at the problem and like know that like this is what you have to do. They're not gonna be like use like implicit differentiation. I can just know to use it. Right? Like,
This you're like really off topic right now.
I'm
Can
sorry.
can
That
can
just, like-
can I just table that
Yes,
until we
yes.
finish this, get through what we're trying to get through? I'd be happy to talk about
Okay.
that, but like
sorry.
that's
It's
okay.
just like you think of it.
Yeah. So that's like my f of x and that's like my L of x, right?
Yes.
So this is what I need to solve. Everybody agree? Okay. So what I'm going to do is I'm going to write this as a compound inequality, and maybe let's start doing this. So far, so good?
Wait, these are a separate equation or a separate problem from the one we just did, right? It's just that the
Yes.
square root of x plus 3 happens.
Sure.
Okay.
Yeah. Just another example. Not necessarily related to the previous one. So what I'm going to do now is I'm going to subtract the square root of x minus 3. Or I'm sorry, square root of x plus 3. But remember, since it's a compound inequality, we have to do it from both places, right? And now I'm going to multiply by the negative. So when I do that, what do I have to remember?
Oh,
Yeah, we have to flip the inequalities. Don't forget to do that.
Wait, you don't do it to both sides.
I
Oh, wait, you just rearranged it.
I did do it to both sides.
Okay,
I just wrote it so that I didn't have to write a minus and then a plus. I just wrote it as a subtraction. Whether you multiply or divide by a negative, you flip the direction of your inequality. And what I'm going to do now is I'm going to graph these three things. Well, I'm going to probably graph them a pair at a time. Let's just graph this part right first and see when this function is below that function. Okay? So I'll pull up my calculator. Because to actually solve this by hand is like a complete nightmare. You could do it algebraically by hand, but it's like, it would take a long time because you have to square both sides. So that means you have to FOIL out with the radical and move everything over and then FOIL again. Yes, Pierce.
Is there a reason why you move the square root of x plus 3 over instead of like adding the other, the lx over? Like, should you move the f of x over?
I think that's usually better because the linear piece is going to be easier to deal with as the common thing between the two. So I have this. And I'm mostly interested in this section where it's below, right? So could care less what's happening before -3. And I don't care about what's happening less than 0. And at 10, that's going to be like what? Make that to 4. Graph again. So this is my square root piece. There's my other piece. So that part is below from here to there, it looks like, right? The straight line is below. So I'm going to find those points. So I have 0.866 maybe. And my other intersection is how do I did what? Yeah. Yes. So I have -266 here. And then I'm going to look at, yes, because that's why what I'm looking for, Emma, is when the linear part is below the square root part, because the inequality says the linear is greater than the square root is greater than the linear. So that's why I'm looking at below. So the inequality part matters, but it just in telling me, like, am I looking for which one above which? So this is like top and bottom. But when I do it here, this would be the top and this would be the bottom. And I'm just looking then using the calculator to help me find the intersections.
How do you find? So you just like it intersects multiple times.
When you're looking for how long and what range of change, then that's
Is it just on the
So here, now what I'm looking at is what? That it's always above, right?
Yeah. That's your answer.
So this part, the green part, is always true, right? So when is this work? Only in between, right? It's basically, this piece is always true, right? So if I do the U or the intersection of those two intervals, well, if I take the intersection of the numbers between 266 and 866 with any real numbers, that intersection is just numbers between -266 and +866, right? So that's what we're saying there. If this was an actual interval, you'd have to look at what the intersection is, right? But it's just like, okay, like, you take the bigger of the two minimums and the smaller of the two maximums, and then you're done. It doesn't matter. Well, yes, you're always taking the intersection, but it doesn't matter if there's like, If there's an infinite, like all real numbers with something else, no, that's fine. Yes, Emma. That's not a point, that's an interval. Those are the x coordinates of where they intersect. The first x intersection is at negative 266, and the second intersection is at x 866. I don't care about the y's. Because it's asking, like, when is, for what values of x is it accurate within blah, 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 blah. So I don't care about the y's. Yes, Pierce.
So for your points down there, where you have an intersection, you're negative infinity, positive infinity, if that was something else, then how would you write there to get a substitute?
So to take the intersection of say this is negative 3 to 6. Okay, so you take the bigger of the two minimums and the smaller of the two maximums. Right? If I think about this on the bigger of the two minimums. That's the bigger. Right? If I think about this so this is negative 266 to 866. And then we have negative 3 to 6. My overlap would be there, right?
Okay. All right.
That's all we're saying. Just basic set stuff, right? When we talk about the intersection where these two things overlap. You're welcome. You too.